Welcome to the Deep Dive. Today we're jumping into something really fascinating, deep in the universe's structure. It's invisible architecture, you might say. We're looking at a huge discovery, finding this mysterious dark object, something with the mass of 1 million suns that we literally couldn't see. And here's the bit that really gets you thinking. Scientists found maybe the smallest dark structure ever detected, mass-wise anyway, using the biggest observation technique possible, gravitational lensing on a cosmic scale. It's like using the whole universe as a magnifying glass to spot, I don't know, a speck of invisible dust.
Okay, let's unpack this a bit.
Yeah, it's pretty wild. What's really striking is just the scale of what they pulled off. They used this global network of telescopes all working together, and they pinpointed an object weighing about 1 million times the mass of our sun, which is just wow. And the big deal here is this is the lowest mass dark thing ever found using gravitational lensing. It's like 100 times smaller than anything they've found before with this method. 1 million solar masses. That's hard to even picture. That's like, what, 100 big star clusters all squished into one dark spot. So, okay, it's dark. We know its mass, roughly. But how on earth do you find its shadow? Isn't that like trying to spot a tiny flaw from, light years away? How do they actually pin down that signal?
Right, you don't see the object itself, you see its gravity. It's all about gravitational lensing. Basically, its immense gravity bends any light that passes close by it. So the researchers were looking for this tiny, tiny distortion. And not just any distortion, but one happening within the image created by an even bigger lens, this distant galaxy, JVAS B 1938 plus 666. The object showed up as just a tiny subtle pinch or maybe a wrinkle in the light from behind it. Think of that background galaxy as a kind of cosmic funhouse mirror. This million solar mass object created this almost invisible flaw on the mirror's surface. Super subtle.
A flicker measured in tiny fractions of an arc second.
Exactly. Extremely small.
Okay, so that explains why you'd need something like an Earth-sized telescope, right? To catch something that faint. They had to link up radio telescopes all over the world using that very long baseline interferometry technique.
That's the one, yeah.
So connecting things like the Green Bank telescope here in the US, the VLBA network, telescopes across Europe, basically turning the planet into one giant lens.
Pretty much, yeah. You needed that massive baseline, the width of the Earth, to get the resolution to see that tiny, tiny gravitational pinch without linking them all up. Impossible.
Got it. Okay, so they found this thing. What could it actually be?
Well, that's the next big question. Its actual identity is still a bit up in the air, but based on its mass, there are two main ideas floating around. It could be a really dense clump of dark matter, what cosmologists sometimes call a subhollow, or maybe it's an incredibly compact dwarf galaxy that's just dark. No stars, inactive. They've pretty much ruled out things like normal star clusters or single black holes.
Okay, here's where it gets really interesting for me, connecting back to the big picture. Why does finding something of this specific size, this million solar mass range, why does that matter so much for understanding the whole universe?
Right. It matters a lot because finding even one object like this is a really critical test and validation. Actually, for the main theory we have about dark matter, the cold dark matter CDM model. See, the CDM theory predicts that dark matter isn't just smooth, it clumps up. It forms this hidden scaffolding, across all sorts of sizes. And that includes these relatively small starless clumps, these subhalos.
Sure.
Models have predicted this whole range of sizes for decades. But actually finding evidence for these low-mass clumps using lensing, that's been incredibly difficult. It was a major missing piece. If they had looked and found absolutely nothing in this mass range, that would have put the whole CDM model into a serious question. It would have been a big problem.
So finding this one confirms a key prediction.
Exactly. The fact that they found one, and its size fits right in with what CDM predicts, it basically tells us that our fundamental ideas about how galaxies form and how structure grows in the universe are, on the right track. It shores up the foundation.
Wow, so we've really pushed gravitational imaging into a new zone here. We're getting better at mapping out that invisible structure of the cosmos. That's a huge leap, technically and theoretically.
It really is. But you think bigger picture. The ultimate aim is to trace out that entire invisible framework, the cosmic web. Which kind of leads you to wonder, right? If finding just this one tiny gravitational wrinkle confirms such a challenging part of the CDM model, what else is out there? What other gravitational hints are we missing, just hiding in plain sight because we haven't looked closely enough or in the right way?
Right. What other unknown million solar mass shadows are out there right now, quietly shaping the galaxies in the universe around us that we just haven't managed to see yet? Something to think about. That's it for this deep dive. Thanks for joining us.